Imagine building a model that rivals GPT-4 for a fraction of the cost. We're talking under $6 million to train a frontier-level AI. That's exactly what DeepSeek just pulled off with V3.
It really is a massive shakeup for the whole industry.
Welcome to our podcast, Artificial Intelligence, Papers and Concepts, curated by Dr. Satya Malik.
Glad to be here for another one.
And just so everyone listening understands the meta context here, both myself and my co-host today are AI-generated voices.
Right, which I think adds a pretty fun layer of irony to what we are discussing today.
Exactly. We are essentially the very technology we are about to dissect. And today we are doing a deep dive into the DeepSeek-V3 technical report.
Yeah, and looking at the specs they published, it feels a lot less like a standard research paper and more like a declaration of war on the idea that you need $100 billion to compete in AI.
I mean, that really is the mission for our deep dive today, right?
Yeah.
We need to unpack exactly how DeepSeek built a mixture of experts model with 671 billion parameters that beats open source competitors and rivals the top closed source models.
And doing all of that while keeping their training costs just shockingly low. It proves that architectural efficiency can actually outmaneuver brute force compute.
Let's start right there with that headline number, because 671 billion parameters is massive. But there's a big caveat attached to it.
There is, yeah.
It's not using all of that brain power at once.
Correct. This is what we call the mixture of experts, or MOE architecture. So while the model does have 671 billion parameters in total, it only activates about 37 billion parameters for any given token it generates.
Okay, let's establish a baseline for everyone listening. In a dense model like Llama 3 or the older GPT models, every single parameter is active for every single word generated, right?
Exactly. The whole brain lights up.
Right. But here, they're saying, we have this massive bench of players, but we're only putting a few on the field at any one time.
That is a great way to put it. Think of it as specialized cognition. If you ask an AI for a pancake recipe, you don't need the neural pathways associated with quantum mechanics firing off.
Right, that would be a waste of energy.
Exactly. By activating only 37 billion parameters, they drastically reduce the computational load per token. And that translates directly into speed and much lower inference costs.
Which brings us to the number that basically broke the internet recently, the training cost. The paper claims they trained this entire massive system on 14.8 trillion diverse, high-quality tokens for what was the exact figure?
The report states the training required 2.788 million H800 GPU hours.
Okay, and if we do the math on that.
Yeah, assuming a standard rental price of about $2 per hour for that hardware, the total training cost comes out to roughly 5.576 million US dollars.
Stick a pin in that number for a second. $5.5 million. I mean, we regularly hear rumors of training runs for models this size costing 50, maybe even $100 million.
Easily, yes.
So is this 5.5 million number just a marketing gimmick? Like, does it actually account for all the inevitable failed runs, the bug fixing, the restarts?
That is the reported cost for the final successful training run. It obviously doesn't account for the entire R&D budget leading up to it, but the paper is quite explicit that the training itself was remarkably stable.
Meaning they didn't have to constantly restart it.
Right. They claim they didn't suffer from those irrecoverable loss spikes that usually plague these massive runs. So while the all-in cost is higher, the fact that you can execute a frontier-level training run for $6 million is the real game changer here.
It's wild.
Yeah.
But before we get into the plumbing of how they actually achieved that, we need to take a quick second to pay some bills of our own.
Sounds good.
This podcast is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai.
Awesome.
Okay, we're back. So we have a massive model, a tiny budget, and probably a lot of skeptical listeners. Let's talk about the architecture. One of the key terms they throw around in the paper is MLA.
Right. Multi-head latent attention. They inherited this from DeepSeek-V3, actually.
Now, attention mechanisms are basically the engine of the transformer, but they are notoriously memory hungry. What is DeepSeek doing differently with MLA?
To understand that, we have to look at the bottleneck in modern LLMs, especially during inference. It's the key value cache, or KV cache.
The short-term memory of the model.
Exactly. Every time the model generates a token, it has to remember the context of everything that came before it. It stores all this in the KV cache. And as your conversation gets longer, that cache absolutely explodes in size.
Right, and it eats up your GPU memory bandwidth.
Which is usually the actual limiting factor when you are serving a model not the compute speed itself.
So the model isn't thinking too slow, it's just struggling to remember everything it just said because the file size of its memory is too big.
That is precisely the problem. DeepSeek-V3 uses MLA to solve this. Instead of storing the full heavy vectors for all those keys and values, they compress them. They project the attention keys and values down into a low-rank latent vector. You can think of it as a zip file for the context, and then they project it back up during the actual attention calculation.
But doesn't compression usually mean you lose information?
Huh.
Like if I zip a photo too much, it gets all pixelated. If they compress the memory, doesn't the model just get stupider?
That's the inherent risk, yeah. But they use a joint compression technique that preserves the essential geometric relationships between the tokens. And importantly, they decouple the rotary positional embeddings.
Wait, break that down for me. The positional embeddings?
It's the part of the data that tells the model where a word is located in the sentence. They separate that from the actual content embeddings. By handling the positions separately, they can compress the content much more aggressively without the model losing the thread of the conversation.
Oh, I see. So they separate the what from the where, compress the what, and then stick it all back together at runtime.
Effectively, yes. The result is a KV cache that is significantly smaller. And why that matters to you and me is that it allows them to serve the model with much larger batch sizes or on fewer GPUs, which is absolutely crucial for making a 671 billion parameter model usable for the public.
That makes a ton of sense. All right, let's move to the experts.
Mm-hmm.
We mentioned earlier this is a mixture of experts model, but the paper specifies they use DeepSeek-Mo with fine-grained experts. How is that different from standard MOE models?
Standard approaches like G-Shard usually use a small number of very large experts. So maybe you have 8 massive experts, and the router picks 2 of them for a token.
Okay.
DeepSeek takes a much more granular approach. They break the experts down into much smaller units. So instead of 8 big generalists, imagine having 64 tiny specialists.
What's the advantage of that? Why have 64 tiny specialists?
Adaptability. It allows for much more flexible combinations of knowledge. But the real innovation here isn't just the size of the experts, it's how they organize them into shared experts versus routed experts.
Shared experts, what does that mean?
In any given sentence, there are certain things the model always needs to process. Basic syntax, grammar, common logical connectors. DeepSeek isolates specific experts to handle this foundational common knowledge, and these shared experts are always activated. They don't even go through the routing process.
Oh, that is clever. So you don't need to waste time asking a specialized physics expert how to use a comma. You just have the comma guy handle it every time.
Exactly. The comma guy is a shared expert. Then, for the highly specific content, the physics equation or the Python code, the router picks the relevant specialized experts. It segregates general knowledge from domain-specific knowledge, drastically reducing redundancy.
Now, I want to touch on something in the paper that sounded really counterintuitive to me. They call it auxiliary loss-free load balancing.
Ah, yes. This is a very deep technical point.
Well, my understanding of MOE models is that you usually run into a problem called routing collapse. Basically, the model gets lazy and sends all the work to just 1 or 2 experts, leaving the rest of the network idle.
Correct. It's like a manager who only trusts one single employee. That one employee burns out doing all the work, and the rest of the team just sits there doing nothing.
Right. And typically, to fix this, researchers add an auxiliary loss, like a penalty. They basically tell the mathematical function, I'm going to punish you if you don't give everyone a turn. It's sort of a participation trophy approach to machine learning.
That is a brilliant analogy. The auxiliary loss forces the model to distribute the load across the experts. But the problem is it forces this balance, even if it means sending a task to an expert who isn't actually the best fit for it.
You trade accuracy for logistics.
Exactly. You are prioritizing a perfectly balanced spreadsheet over actually getting the correct answer.
So DeepSeek decided to just remove the participation trophy entirely.
They did. They ditched the auxiliary loss. Instead, they use a dynamic bias term for the routing mechanism.
How does a bias term fix it?
It's subtle but profound. The auxiliary loss changes the gradient during training. It actively changes what the model is learning, which can confuse the primary learning signal. The bias term, on the other hand, just changes the decision at the exact moment of routing.
Like a nudge.
Yes, exactly like a nudge. If expert A is getting overloaded, the system temporarily lowers expert A's bias score by a tiny fraction. It just makes expert A look slightly less attractive to the router for that specific step. And if an expert is underloaded, it raises their bias.
So it tricks the router into picking someone else, but without actually altering the fundamental learning objective of the model.
Precisely. They found that this auxiliary loss-free method consistently achieved better performance because the model gets to focus purely on predicting the right token, rather than constantly worrying about satisfying a load balancing quota.
This whole theme of risky but rewarding engineering just seems to be the defining story of V3. And honestly, nothing screams risky quite like their choice of numerical precision.
Oh, absolutely.
They trained this entire massive thing using FP8 8-bit floating point numbers.
Which is perhaps the boldest move in the entire technical report. This is the first time we've seen FP8 mixed precision training validated on an extremely large-scale model.
For those listening who might not be GPU engineers, usually these frontier models are trained in BF16 or FP16, 16-bit numbers. Moving down to 8-bit is like, well, it's like trying to paint a highly detailed masterpiece.
Yeah.
But you only have 256 colors on your palette instead of 65,000. You lose all the nuance.
You lose dynamic range, yeah.
Yeah.
The major risk with 8-bit training is that the numbers can get too small and just vanish, which is called underflow, or they get too big and crash the system, which is overflow.
Right.
And in a massive neural network, that usually leads to extreme instability. The loss function spikes, your training collapses, and you have to roll back and restart.
So how do they prevent the model from just crashing constantly?
They used a technique called fine-grained quantization. Specifically, they used tile-wise grouping for the activations and block-wise grouping for the weights.
Okay, you're going to have to break that down for me.
Sure. In a standard tensor matrix, you might have one massive outlier number, a huge activation spike. If you try to fit that entire matrix into a limited 8-bit scale, you have to squash all the other smaller numbers down to near zero just to make room for that one giant outlier.
So you lose all the detail in the small numbers. One bad apple ruins the resolution for everyone.
Exactly. So DeepSeek breaks the tensors down into tiny tiles, say 1 by 128 elements, and they scale each tiny tile independently.
Oh, wow.
Yeah. So if one tile has a huge outlier, it only squashes the resolution for that specific group of 128 numbers. The rest of the matrix gets to retain its high precision.
But doing that on a micro level across hundreds of billions of parameters, that has to be incredibly tedious for the system to manage.
It adds software complexity, for sure, but the payoff is immense. Faster math, significantly lower memory usage, and they actually went even further. For the accumulation phase, when the GPU is actually adding up the results of the matrix multiplication, they promote the numbers back up to high-precision float 32 inside the CUDA cores.
So they store the data and move it around in cheap, fast 8-bit format, but they do the actual heavy math in high-precision 32-bit.
You nailed it. It gives you the best of both worlds. You get the memory bandwidth and the speed of FP8, but the numerical stability of FP32. This is exactly why they were able to train on nearly 15 trillion tokens without the model collapsing. No loss spikes, no rollbacks.
Unbelievable. Now, speaking of moving data around, we have to talk about the dual pipe algorithm. The paper makes a really big deal out of how they overlapped computation and communication.
And they should make a big deal of it. This addresses the harsh physical reality of training on over 2,000 GPUs. When you have a MoE model, you are constantly shuffling data back and forth between different GPUs because your different experts physically live on different cards.
Right, the all-to-all communication bottleneck. Because while the data is traveling through the network cables, the GPU compute cores are just sitting there, twiddling their thumbs, waiting for the data to arrive.
That's the standard problem. We call them pipeline bubbles. Dual pipe is a custom scheduling algorithm DeepSeek created to overlap the forward and backward passes of different microbatches.
How does that look in practice?
Think of it like a kitchen. You don't chop the vegetables, wait 10 minutes for the water to boil, and then start cooking. You chop the vegetables while the water's boiling. You are doing two things at once, so there's no waiting around.
So they structured the training steps so that whenever the network cables are busy sending data, the compute cores are busy crunching the math for a completely different part of the model.
Yes, they achieved near zero communication overhead with this. The waiting time was effectively hidden completely behind the working time.
Which is huge for scaling, right?
Critical. It means that as they add more GPUs to the cluster, their efficiency doesn't drop off. Linear scaling is the holy grail of distributed training, and dual pipe brought them very, very close to it.
It's amazing how much of this AI breakthrough is actually just extreme, hardcore systems engineering. But let's pivot to the software side of things. There's a feature here called multi-token prediction. or MTP.
Yes, MTP. This is a really fascinating architectural choice. Standard language models predict the next token, just one, T plus 1. DeepSeek-V3 predicts the next token and the token after that sequentially, T plus 1 and T plus 2.
Well, why do that? Is it just showing off? Like, I know what you're going to say before you even say it.
Not at all. It forces the model to actually plan ahead. If I only have to predict the very next word, I can sometimes get away with a pretty superficial understanding of the context. But if I have to predict the second word as well, while maintaining the causal chain, I need a much deeper grasp of the sentence structure and the underlying logic.
It densifies the training signals.
Exactly. It gives the model significantly more feedback per step.
It's like playing chess. Thinking one move ahead is relatively easy. Thinking two moves ahead requires actual strategy.
That's a perfect way to look at it. And the truly brilliant part is what they do during inference when you are actually using the model. They can completely discard the MTP module to save time, treating it just as a training scaffold. Or they can keep it and use it for speculative decoding.
Speculative decoding is where the model drafts a future token and then verifies it, right?
Yes. Since the MTP module has already guessed what the second token will be, if that guess turns out to be correct, you basically get 2 tokens for the price of 1 computation cycle. Yeah, they claim a 1.8x speedup in text generation simply by utilizing this speculative decoding feature.
Okay, so we've covered the cost, the extreme plumbing, and the training tricks. But the ultimate question is, does the model actually work? Or is it just a very cheap, very efficient generator of nonsense?
The benchmarks are pretty undeniable. On standard knowledge tests like MMLU and MMLU Pro, it is at the absolute top of the class for open source models. But where it really shocks the system is in math and code.
Really?
Yes. On the Math 500 benchmark and live code bench, DeepSeek-V3 is an absolute beast. It outperforms all open source models and rivals, and in some cases beats GPT-4o and Claude 3.5 Sonnet. Oh, and for Chinese language tasks, it significantly outperforms GPT-4o on Chinese simple QA.
Which brings us to the R1 connection.
Yeah.
The paper mentions they use DeepSeek R1 to help train V3. This is the distillation process they talk about.
Yes. This is the secret sauce for V3's reasoning ability. DeepSeek R1 is their specialized reasoning model. It's one of those models that uses chain of thought, where it essentially talks to itself for a long time, verifying and reflecting to solve a complex problem.
Right, but V3 is designed to be a fast, general chatbot. It doesn't have the luxury of sitting there and pondering for 20 seconds before it answers you.
Precisely. So they used R1 to generate massive amounts of synthetic data, millions of reasoning traces. And then they trained V3 on that data. But here's the key. They didn't just blindly copy R1's long-winded internal monologues.
How do they filter it?
They carefully curated the data to teach V3 the underlying patterns of reflection and verification, basically teaching it how to check its own work, but ensuring the output remains concise. They wanted to avoid the overthinking spiral that pure reasoning models get stuck in.
So V3 essentially learned the instincts of the reasoning model without inheriting all the latency.
Exactly. It's knowledge distillation in its purest form. They took the smarts of a heavy, slow model and injected them directly into an efficient, fast architecture.
Fascinating. Now, before we wrap up, I have to mention the section of the paper titled Suggestions on Hardware Design. Reading that, it felt a little bit like they were lecturing NVIDIA.
It was definitely a very public feature request, yes. They effectively told the hardware vendors, look, your communication protocols are inefficient for what we are doing.
They specifically asked for a dedicated network coprocessor, didn't they?
They did. So the main calculation cores, the SMVs, don't have to waste time handling data routing across the network. And they also pointed out that current chips don't natively support high-precision accumulation for FTA.
They're basically saying, we had to build all this incredibly complex software, the tile-wise quantization, the dual-pipe algorithm, because your hardware isn't actually optimized for frontier AI training.
It highlights a really important trend. We are hitting the physical limits of current silicon design. The software engineers are now having to design the next generation of chips by proxy, simply by publishing their pain points.
So let's pull back to the big picture here. We have a frontier model that only costs $5.5 million to train. It uses sparse experts to run efficiently, it uses 8-bit math to save memory, and it rivals the trillion-dollar tech giants. What is the ultimate takeaway for you?
The takeaway is that the moat of pure capital is evaporating. For the last 2 years, the underlying assumption in the industry was that only Google, Microsoft, and OpenAI could play this game because the entrance fee was billions of dollars in raw compute. DeepSeek-V3 proves that assumption is false.
The entrance fee is intellect and engineering, not just massive piles of cash.
Precisely. If you can optimize your architecture, if you can solve routing collapse without an auxiliary loss, if you can master FP8 stability, you can compete at the absolute frontier for a fraction of the price. The moat isn't money anymore, it's algorithmic efficiency.
And that is both a terrifying and exciting prospect for the industry. I mean, if an open source model can rival GPT-4o for $6 million today, it really makes you wonder what happens next.
It opens up entirely new possibilities.
Exactly. Which leaves me with a thought for our listeners to mull over. We talked about how this shatters the proprietary moat of the big labs. But if you extrapolate this trend of extreme efficiency, what happens when the cost to train a frontier model drops from 6 million down to, say, 600,000?
Oh, that changes everything.
Right. Are we approaching a future where individual universities or even decentralized crowdsourced communities can pool their resources to train bespoke, frontier-level AI models entirely outside the corporate ecosystem? When AI development is no longer gated by giant data centers, the power dynamics of the entire tech world shift completely.
That is a profound thought to leave on. The hardware wars might be loud right now, but the software efficiency revolution is where the real democratization of AI is going to happen.
Absolutely. I want to thank you for joining me, and thank you to everyone listening for tuning in to this deep dive. We hope you enjoyed getting into the weeds of MLA and FP8 as much as we did. If you want to keep up with these tectonic shifts in AI, make sure to subscribe so you don't miss our next breakdown. Until next time.